Namaskar students. In our previous video, we have discussed about Lagrange's method of undetermined multipliers and we have done one problem also. So continuing the same, let us take one more question based on Lagrange's method. So the problem is prove that the stationary values of u, the function u is given here, subject to two conditions which are Lx plus my plus nz equal to 0, and the second condition is x square upon a square plus y square upon b square plus z square upon c square equal to 1. So these are two conditions, and what we have to prove? We have to prove that the stationary values of the given function, which is u, are the roots of this equation. L square a raised to power 4 divided by 1 minus a square u plus m square b raised to power 4 divided by 1 minus b square u plus n square c raised to power 4 divided by 1 minus c square u equal to 0. If we compare this problem with the previous one which we have discussed in the last video, what is the difference here? If you will observe, in the previous question, we were having only one condition, we were having only one constraint, but here we are having two constraints. One is Lx plus my plus nz equal to 0, and the another is x square upon a square plus y square upon b square plus z square upon c square equal to 1. So as we have discussed in our previous video, while defining the function h here, we will be considering two Lagrange's multipliers, which you can take as lambda 1, lambda 2, or whatever you want to take, because that is just notation. You can take it in the form of lambda and mu. So you can take it in any form because it is a notation, but we will be considering here two multipliers. And we have to derive this equation. We have to show that the stationary values are the roots of this equation. So somehow we have to derive this equation which is given in the last in this slide. So let us start this problem. First of all, let us write whatever is here given. We have u is given. U is x square upon a raised to power 4 plus y square upon b raised to power 4 plus z square upon c raised to power 4. Let us name this as equation 1. This is the function about whose stationary points we are talking in this question, and it is subject to the first condition is Lx plus my plus nz equal to 0. Let f is equal to Lx plus my plus nz. Let us name this as equation 2. And another condition is here x square upon a square plus y square upon b square plus z square upon c square equal to 1. Let us name this as equation 3, and let g as x square upon a square plus y square upon b square plus z square upon c square minus 1. Let us define the function, new function. Consider a function, say h, as h equal to u. U is a function whose stationary points we have to find out. plus first Lagrange's multiplier, which we have taken here as lambda. Then for the first condition, we have assumed Lx plus My plus Nz as f. So f. Let us take the second multiplier, Lagrange's multiplier, mu, and here we have taken notation of G. So G. Now for stationary values of u, we have partial derivative of h with respect to x as 0, then del h by del y as 0, and del h by del z as 0. That is, if we see the definition of h, which is written here, this one, from here, what will be del h by del x? Del u by del x plus lambda, then del f by del x plus mu, then del g by del x equal to 0. Similarly, the expression for del h upon del y will be del u by del y. Now partial derivatives will be with respect to y. Then plus lambda. How we are evaluating, how we are writing these expressions? With the help of this function h. This one. We are differentiating this function h partially with respect to y. Lambda del f by del y plus mu del g by del y equal to 0. And similarly, we can write down del h by del z. It will be del u by del z lambda del f by del z plus mu del f by, it will not be f, it will be, we have written it wrong, let us correct it. It will be, let us see h, what we have g. So it will be, it is here mu g. So it will be mu, then del g, and we are differentiating it partially with respect to z. So it will be del g by del z equal to 0. So we have these three equations. Let us put here f and g, these partial derivatives. We have, let us start with the first one. This del u by del x, we know that u is given by equation 1. So we can evaluate del u by del x. It will come as 2x upon a raised to power 4. Then we need del f by del x. It will be evaluated with the definition of f. So del f by del x will be L, and from this my and nz we will be getting 0. Then we need del g by del x. Del g by del x will be evaluated from the definition of this function g. From here, from this g, we will be getting del g by del x as 2x upon a square. So we will be putting all these three partial derivative in this equation, So it will be 2x upon a raised to power 4. The next term is lambda del f by del x, which is L, Then we have plus mu del g by del x, which will be 2x upon a square equal to 0. And we will be naming this equation as equation 4. Now, if we find out this one when we are differentiating partially with respect to y, we will obtain 2y del u by del y will be 2y upon p raised to power 4, then lambda, then del f upon del y, it will be obtained from equation this one, f, from the definition of f, del f upon del y will be m plus Lagrange's multiplier mu, then del g by del y, which will be 2y upon b square equal to 0. And let us name this as equation 5. Now let us find this one, del u by del z plus lambda del f by del z plus mu del g by del z equal to 0. Here all partial derivatives are with respect to z. So it will be 2z c raised to power 4, 2z divided by c raised to power 4. Then it is lambda n plus mu, and it will be multiplied with 2z upon c square. This is del g by del z equal to 0. And let us name this as equation 6. Now with the help of equation 4, equation 5, this one, then this equation 6, and the two given conditions which we have named as equation 2 and equation 3. We will be trying to derive this equation which you have to prove. And if you will see, this equation involves u. The roots of this equation will be giving the stationary values of the function u. So with the help of 5 equations, equation 2, equation 3, which are the given constraints, and these equations 4, 5, and 6, we will be trying to derive the result. We will be trying to prove the result. Now, if we see these equations 4, 5, and 6, if we multiply equation 4 with x, then here this term will become Lx. If you multiply equation 5 with y, this term will become my. And if you multiply equation 6 with z, here this term will become nz. And after doing this, if we add all the 3 equations, we will be having Lx plus my plus nz. And we know that Lx plus my plus nz is equal to 0 because this is our condition It is given in our problem. We have named it as equation 2 also. So by doing this, we will be able to find a relation which will be having only mu, which will be free from lambda, because Lx plus My plus Nz will become 0. So let us try this one. Multiplying equations 4, 5 and 6 with x, y and z respectively, and then adding, we have 2 x square upon 8 raised to power 4. Let us write down this equation directly. It will be 2 is common in first terms in all of these equations. So we can take this 2 common. If we take 2 common, we will be getting x square upon 8 raised to power 4 plus y square upon b raised to power 4 plus z square upon c raised to power 4. Then we have lambda common, Lx plus My plus Nz. This we have already discussed. And if we see the last term of all these three equations, then this 2 mu is common. So if you take this 2 mu common, we will be having x square upon a square plus y square upon b square plus z square upon c square. And since the right hand side is 0, it will again be the same 0. That is, now if we see this expression, this is the same expression which we have for u. So we can write here u. And as we have discussed already, this is our first condition which we have named as equation 2. This is equal to Lx plus My plus Nz is equal to 0. This 2 mu, and this expression x square upon a square plus y square upon b square plus z square upon c square, this is also present in our second condition, and by the second condition this is equal to 1. So considering it as 1, it's equal to, the right hand side is 0. So what we get from here, we get that the second Lagrange's multiplier, which is mu, it is coming as minus u. And let us name this as equation number 7. Now, what we can do further for proving the result, we have second and third equation with us, and we have obtained that mu is equal to minus u. So if we put here mu in equation 4th, then we can find out lambda. We can find out x, not lambda. We can find out x, and that x will be in the terms of lambda. So let us put here mu as minus u in equation 4 and solve it for x. Similarly, by considering mu as minus u in equation 5, we will be solving for y, and in equation 6, when we will be putting mu as minus u, we will be solving for z. putting mu equal to minus u. Let us check the number of those equations 4, 5 and 6. Putting mu equal to minus u in equations 4, 5 and 6, we have from fourth equation we will be getting x, and x will be minus e raised to power 4 lambda L, this divided by 2 1 minus a square. It's a simple calculation, and y will come as, from equation 5 we will get y, and this y will be minus b raised to power 4 lambda m is divided by 2 1 minus b square u, and z will be, in this we will be using equation 6, minus c raised to power 4 lambda n is divided by 2 1 minus c square u. Now we have x, y, z. If we use this x, y and z in equation 2. Why we are using this equation 2? Because here right hand side is 0, and it is simpler one, lx plus my plus nz, because now we have x, y and z with us. So just multiply x, y and z with l, m and n, and then consider their sum. It will be lx plus my plus nz, and using this result, this first condition, we will be able to eliminate lambda, and in doing this we will be obtaining this equation, which is our required equation. So let us do this. Putting x, y and z in equation 2. Equation 2 is our first constraint, lx plus my plus nz equal to 0. We have lx, it will become minus sign, a raised to power 4 lambda lx, so it will become l square. Then in denominator we have 2 1 minus a square u. The next term in equation 2 is my, so it will be minus b raised to power 4 lambda m square to 1 minus b square u, minus, then we have nz, which will be minus c raised to power 4 lambda n square divided by 2 1 minus c square u, and the right hand side of equation 2 is 0. If we simplify this, here lambda by 2 is common, we will get a raised to power 4 l square 1 minus a square u. We have taken minus sign outside, so the next term will be this b raised to power 4 m square is divided by 1 minus b square u, and here we will be having c4 c raised to power 4 n square 1 minus c square u equal to 0. Now here lambda is Lagrange's multiplier and hence it is non-zero. So this is only possible if this expression which is written within the bracket is 0. So here lambda is not equal to 0. So we get a raised to power 4 L square 1 minus a square u plus b raised to power 4 m square 1 minus b squared u plus c raised to power 4 n square 1 minus c squared u equal to 0. And this equation gives the stationary values of u. And this proves our result, our problem. So thank you. Have a nice day.